All right, so welcome back everybody for today's session of the Cardiff analysis seminar. So before we start, a small announcement. So next week, exceptionally, we will start our seminar at 3:10 p.m. as opposed to 2:10 p.m. So 1 hour later, just to make it less cruel on our speaker from California. So next week, 3:10 Greenwich Mean Time. So, but today we are delighted to have Rudi Weikard from University of Alabama at Birmingham, who will talk about rough coefficients in ordinary differential equations. So without further ado, over to you, and thank you very much.
All right, thank you for giving me this opportunity. It's a pleasure to be back in Cardiff in some ways. All right, so I'm reporting on joint work with my students, and in case of Ahmed, former student. This is Kevin, Ahmed, Min, and Stephen. And I'll begin with telling you about what spectral theory is about. Of course, most of you know this, but anyway. So in 1822, Fourier wanted to describe heat conduction in a rod, so spatial, one-dimensional, and you have the heat equation, and there are some boundary conditions which, so phi is the temperature at a certain time and a certain place in space, and the boundary conditions mean that the ends of the rods are insulated, and then we have a certain initial condition at time 0. There's a certain temperature distribution. And the question is how to tell what the temperature is going to be at some later time. So how you do this, we all know, you separate the variables. That leads to the introduction of a separation constant, which is called lambda. And then the spatial equation will look like this in this particular case. This very simple differential equation. These boundary conditions, of course, are inherited from these ones here. And this equation is simple enough, even for me, so that I can solve it. The solutions are sines and cosines. You take into account the boundary conditions, and you find that you have to, that the solutions are just the cosines, and that the numbers kn here have to be chosen in precisely this way in order to satisfy the boundary conditions. So now you also take into account the time differential equation, which is going to be a first order one, and you get the solutions of the heat equation satisfying those boundary conditions. They are right here. But the question is, what could we now do about these initial conditions? I mean, unless you're extremely lucky, none of these solutions will have those right initial conditions. If you put t equals 0, it should have to look just like this cosine. So fortunately, our initial condition, phi naught, so this is the initial temperature distribution, if it's a square integrable function. It may be expanded into eigenfunctions. So the cosines, of course, are the eigenfunctions, and there are coefficients called Fourier coefficients, so that the function almost everywhere is given by this series. And because of linearity and everything converges nicely and so forth, you can now write down the solution to the initial boundary value problem. It's given right here. So this solves the differential equation, the boundary conditions, and also the initial conditions. So to do things like that is one of the major themes of spectral theory. So when we do spectral theory, this is one of the goals we have in mind, to be able to do such a thing. All right, so there are some generalizations. This is just about 200 years ago. So first, shortly after Sturm and Liouville, they allowed for more general coefficients here. They were still working on a finite interval. This is, of course, the famous Sturm-Liouville equation. While in 1910, considered how to deal with a half-line, and they introduced the famous limit point and limit circle classification. in the 1920s, so that's now 100 years ago, Birkhoff and Langer first looked at systems of first-order equations. Krein in 1952 was the first one for whom the coefficients in the equation were not just functions like they are for Sturm and Liouville. So he had p equals 1 and v equals 0, but r was a positive measure. In 1999, Savchuk and Shkalikov studied the Schrödinger equation with the distributional potential. So p was 1, r was 1, I think, but v was a distribution. And this paper actually, it created a lot of interest. So there were many papers after that doing similar things. So it had quite some impact. But in 2013, Eckart, Gastesi, Nichols, and Teschel, they told us how to deal with these kinds of equations without ever mentioning distributions, because you can do this also with quasi-derivatives, and then all the functions you're dealing with are just locally integrable functions. So you don't have to really go into distributions if you want to have a distributional potential, say in the Schrödinger equation. So there are many other applications, higher order differential equations, difference equations, quantum graphs. And there are many more people involved in this. I mean, this subject has over the 200 years, tens of thousands of papers at least. And I mention here Feller, Katz, and Atkinson, but I'm forgetting most people. All right. So as my title indicates, I'm looking for generalizing to rougher coefficients. So let's have a look at this differential equation. You can think of it as a scalar equation for now. And so if the coefficients R and G are analytic, then you can expect that U is analytic. And if R and G are continuous, then you can expect that U is continuously differentiable. The solution U is continuously differentiable. So I've gotten here a lot rougher from analytic to continuous coefficients. So you can do a bit better here. You can have R and G locally integrable, and then you can you have that U is locally absolutely continuous. So how far can you go? Well, if R and G are distributions of order 0, then U is going to be locally of bounded variation. I will say a little bit more about that in case there are people who are not so familiar with the distributions. I will say a little bit more in a few minutes or seconds maybe. So now you could, of course, think, okay, we'll make R even rougher. We'll take it a distribution of higher order, just any kind of distribution, but then it's going to be difficult to define, or maybe impossible to define this product RU, because if R gets rougher, then U will also get rougher, and it's not going to be a function anymore. It's going to be also a distribution. And the product of distributions cannot be defined. So it seems that this is sort of the canonical sort of condition to have, that the coefficients of the differential equations are distributions of order 0, and you cannot go further. One should never say this perhaps, but that's my feeling here. And the reason is that one cannot define these products. All right, so in the hypothesis we are putting are as follows. So we are looking at this differential equation. Of course, you can think of the Q minus W lambda as R. Maybe you have to multiply with J inverse or something. So this looks little bit more difficult than the previous equation, but it's essentially that sort of differential equation as a differential equation. So we pose it on a real interval AB, and we require the following. So our systems and matrices J, Q, and W are n times n matrices. J is constant, invertible, and skew-hermitian. Q and W are Hermitian distributions of order 0. And W is a non-negative distribution. And I'm telling you in a moment how all these things are defined. So that means you can define a Hilbert space L2W, and you have a scalar product, which is then defined like this. So W being a Hermitian a positive Hermitian distribution can also be considered as a measure. So that's why I wrote this integral here. So if you want to do spectral theory for self-adjoint or symmetric, in symmetric settings, self-adjoint, then these are sort of canonical conditions. And at the very end, I have to add some more technical conditions, but I'll point that out at that time. All right, so let me first say a few words about distributions. So first, what is a distribution? It's a linear functional on the set of test functions. These are infinitely often compactly supported functions on our interval AB. So, and the linear functional on these test functions is called the distribution if you have this condition satisfied. So for every compact set K, there exists constants C and K, such that you have this inequality whenever phi has its support in K. Okay, and the simplest examples are just a locally integrable function gives rise to a distribution. Because phi being compactly supported, this integral really is only over the support of phi, and which is contained in a compact set. And therefore, f is integrable over there. And you find that this is a distribution of order 0. In fact, you take the sup of phi out of the integral, and you have a distribution of order 0. The other one is here, this simple distribution, also of order 0. And of course, it gives rise to the Dirac delta function. Okay, so I think I hadn't defined what the order 0 means. Here it is. So this integer k, if it can be chosen independently of the compact set k, then you have a distribution of finite order, and the smallest k that will do is called the order of the distribution. So in this case, we can do, in these two cases, we can do with k equals 0. And the nice thing about distribution is that every distribution has a derivative, which is defined like this. And they also have antiderivatives. In fact, they have many antiderivatives, but just like we are used from calculus, if you have two antiderivatives, then their difference is a constant. And the constant is, we associate with locally integrable functions, f. We call this distribution also f. So in that sense, with the locally integrable function, the constant function here, we associate the same distribution. So in that sense, it's constant. All right, so there's a connection with the functions of bounded variation. It goes like this. So a function of locally bounded variation generates a complex Lebesgue-Stieltjes measure, which I call dq. The function is called q. I should have said that here. The measure is then called dq. That's not a measure, it's only a measure on every compact subset of AB. It may not be a measure on all of AB. Okay, and then you can define a distribution just like this. So again, the phi having support only on a compact set means that dq is actually a measure there, and therefore this integral here is defined and gives you the distribution of order 0. And the two examples I had earlier are actually special cases of this. In one case, q is an absolutely continuous function, and dq is equal to, say, f dx. And in the other case, q is the Heaviside function when dq is the Dirac delta measure. Okay, now the Riesz representation theorem says that not only is are all these distributions of order 0, but these are all the distributions of order 0. So whenever you have any distribution of order 0, then there's a function of locally bounded variation Q, such that the distribution is given by such an integral. Okay, so the derivatives of functions of locally bounded variation are precisely the distributions of order 0. Still, I'm a little bit ahead of myself. Why do I say the derivatives? So this distribution here is an antiderivative. It's given by this. So that's Q itself is a distribution. And then this distribution is the derivative of Q in that sense. And we use these notation here interchangeably. So now comes the important point. If Q is a distribution of order 0 and U is locally integrable with respect to the total variation measure introduced by dq, then we can define that Q times U of phi as the integral of phi U dq. So phi times U is going to be just an integrable function, integrable with respect to this measure dq on the compact set. So we can define this product, but for this to do this, U actually has to be a function of this nature, and that's the key. So if you are rougher than that, you get into trouble. So since we are talking about matrices, let me say a few things about what to do, what these words meant I said earlier. So first we define the conjugate of a distribution. It's defined like this. And if we now have an n times n matrix, all of whose entries are distributions of order 0, then we define Q star in the usual way. So the jkth element of Q star is the kjth element and the conjugate of that. The conjugate I've just defined up here. And of course, Q is called Hermitian if Q is equal to Q star. Then I should say a few words about positive. So a scalar distribution is called non-negative or positive, if you like, if the values of Q are always non-negative as soon as the test function that doesn't take any negative values. So any non-negative scalar distribution is necessarily of order 0 and therefore represented by a positive measure. And for matrix value distributions, we just look at, we take a vector A and Cn, and we form this scalar distribution, and we ask it to be non-negative for every such choice of a vector A and Cn. And so this is how the matrix valued distributions are defined to be non-negative. All right, now let's look at differential equations. We will run into one particular problem. Now let me first say this here. So here's our differential equation, just the one I had before. And now let's look at all the terms. So U will seek solutions among the locally bounded functions of locally bounded variation, and then U prime is going to be a distribution of order 0, as I just said. And we can.
You said, can I ask on the last slide? Can you show the last slide?
Yeah, probably, yes. This one?
Yeah, they said any non-negative distribution is of order 0 and represented. But what about delta distributions? Then it's.
Yes, delta distribution is one of them. Yes, it is a positive measure, no?
But it's not a measure. So it's of order 1.
No, that's delta prime, which is of order 1. Delta is of order 0.
Mm-hmm.
So here, this is the delta distribution. If you know what the sup of phi is, the case k equals 0, that's completely enough.
Okay.
All right, so I have defined, so U being of bounded variation means that it is locally integrable because it's bounded. And if I let F to be an L1 log of W, then this product is defined. So all these products are defined and each one is a distribution of order 0. And now you can ask for a given function U, is this satisfied or not? And if it's satisfied, you have a solution. If it's not, you don't. So that is how these differential equations are to be interpreted. Now we will look for balanced solutions only. There are maybe other kind solutions. So if you have a function of bounded variation, then it has right-hand limits and left-hand limits. You call F plus and F minus. And now I fix a number t and I form these combinations here. And I have now two such functions and I want to integrate by parts. Half of spectral theory is integrating by parts. So we have to have an integration by parts formula. And here it is. You have the integral here, you have the boundary terms. Unfortunately, in general, you have also another term in this integration by parts formula, and you don't like that. So this term here, this integral will disappear if the jumps of the function g do not coincide with jumps of the function f. Then this integral disappears and you don't have to worry about it. We don't want to make any such assumptions, so we cannot assume that this integral disappears, but here's this term. If you choose t equal 1/2, you don't have to worry about this integral. So if t is equal to 1/2, we have just the average of the right-hand and the left-hand limits for our functions, and these functions we call balanced functions. All right, so now there's a trouble with the continuation of solutions in case your measures have atomic parts. So and you can look at this in the simplest of all cases. You have u prime is alpha delta 0, so this is the delta measure or delta distribution times u. And so let's solve this equation. If we have a test function to the left of 0, then delta of the test function is going to be 0, and therefore u prime is going to be 0, and that means u is a constant, which I call ul, and on the right of 0 you have the same, I call it ur. And then if you look at test functions which straddle the point 0, then you get that this equation also has to be satisfied. So it's very simple, good exercise. Now, if u is left continuous, that means u of 0 is equal to the limit from the left. So u of 0 is equal to ul. Then plug this in here and you can, if you know the value ul, if that's your initial condition, then you can figure out what ur is regardless of alpha. However, if u is right continuous, you cannot do such a thing. Not generally anyway. So if alpha is equal to 1, you will be in trouble. There's trouble there when alpha is equal to 1. So for left continuous solutions, you can find unique solutions if you're looking towards the right, and right continuous solutions, you can solve this initial value problem if you're only looking towards the left. For balanced solutions, you're in trouble either way. So you're in trouble if alpha is 2, or if alpha is minus 2, you're in trouble. So that's something we have to contend with. So the troubling points are these ones here. So our differential equation looks a little bit more difficult than this one here. Therefore, our alpha here is now a matrix and looks like that, or 2 minus alpha, perhaps this quotient here looks like that in general. Delta Q here is the measure at the singleton, or you can take, so R is the antiderivative of the distribution little r. So you have the right-hand limit minus the left-hand limit. So these are these numbers. Of course, the delta Q's are going to be 0 almost everywhere because you can have jumps only in countably many places. So you have countably many places where this could be different from 0, and countably many places where this could be different from 0, making for countably many places. Probably talking a little bit too much. Anyway, if these matrices are invertible, then there's no trouble. Then existence and uniqueness exists is okay for initial value problems. So let's look at the bad points. We introduce two sets. First, we take, for fixed x, we take all the values of lambda for which one of these two matrices has determinant 0. That means it's not invertible. And we also look at the set for fixed lambda of all x where this happens. So they collect somehow the bad points. And then we have some facts. So first of all, as I just mentioned, lambda sub x has to be empty for all but countably many x, because you can have jumps only in countably many places. If lambda sub x is not empty, then it is either a finite set or it is the full plane. There's no other option. And even if all the lambda x are finite, then their union may still be a dense set in C, of course. The set Xi lambda is discrete, and the union of all the Xi lambda may be dense in A. All right. So now another important thing we need in our, well, you need that even if you look at constant coefficient equations. So if as soon as you talk about systems of differential equations, you may have to deal with relations rather than with operators as we are used to. So there's some historical note here, but the linear relations have by now also made it in some books. All right, so you all know what the relation is. It's a subset of some Cartesian product of two sets. But we are interested in linear relations, so you have to have maybe vector spaces. We are only interested in Hilbert spaces. So you have a Cartesian product of two Hilbert spaces. And then if you have a linear subspace of that, then that's called a linear relation. And they have a domain, a range, a kernel. They're defined like here, not very surprising. And of course, an operator is a special kind of relation, namely if you have, for any u, you have to have a unique f in the range, of course. So we are thinking of operators. If you're talking about operators, we're thinking of them as graphs rather than as operations, maybe. All right, the nice thing about relations is that they always have an inverse and an adjoint. You don't have to worry about the thing. Every linear relation has an inverse. Every linear relation has an adjoint. And they are defined here. And of course, the definition of the adjoint conforms with the one we're used to from the linear operator theory. So we will actually be interested in the case where H1 and H2 are the same. S star, S is a relation in H1 cross H2, S star is in H2 cross H1, but if they are the same, then they live in the same space. And therefore you could ask, is one a subset of the other? And if so, then S is called symmetric. And if they're even equal, then S is called self-adjoint. All right, then we talk about resolvents. So now E is a closed linear relation in H. And we define E minus lambda by this. So it's very natural. And then you look at this set, is the set of all those lambda where the kernel of E minus lambda is trivial and the range of E minus lambda is everything. If you have such a lambda, then it's in this set. This set is the resolvent set and its complement is the spectrum. So one of these two things goes wrong if you are in the spectrum. And the inverse relation of E minus lambda is going to be always an operator if lambda is in the resolvent set. But it may not be densely defined. So it's just a relation. In a relation, the domain of the relation does not have to be the full space. It's just some set. So that's something you don't have to worry about if you do the theory with linear relations instead of linear operators. So you have the usual resolvent relation, just as in the usual case, and you also have the fact that the adjoint of R lambda is the resolvent for lambda bar. So then we have extension theory. So if E is a closed symmetric linear extension, we have deficiency spaces as defined here. And you can prove that the dimensions of these spaces are constant in the upper half plane and in the lower half plane. And these dimensions you call deficiency indices, and you denote them by n plus minus. They come up in the future. And then we have this von Neumann's formula that any closed symmetric relation, we have that its adjoint, which is a superset of E, is given by E plus direct sum with these deficiency spaces. And this sum is even orthogonal if you choose lambda to be I or minus I. All right, so these were preparations. Now we come to the actual matter of the talk. So first, it is going to be important to distinguish between a space of functions and a space of classes of functions, where at least in my real analysis course, we brush over these things oftentimes for good reason, but you cannot do so here. So if W is a non-negative matrix valued measure, and then that means that F star WF is a positive scalar measure for any measurable function F. And then we define curly L2 is the space of all measurable functions F, such that F star WF is a finite measure. And we have a semi-scalar product in this case, very simple. But you can have a non-trivial U such that the scalar product with itself is not is equal to 0. And therefore you introduce now the Hilbert space by quotienting out this set of 0 norm things. Oops. Okay, so I call this straight up L2W. So that's the Hilbert space. Curly L2W, of course, is not the Hilbert space. All right, now we define maximal relations. So we have an equation, a solution of our equation. This is our equation here. So we have a pair UF, both are functions in L2W, it's in curly L2W. And if you plug them in here, then you have this satisfied in the sense of distributions, as I explained earlier. Now, if you have such a pair UF, then you can take their classes, and you have then a pair of elements in L2W times L2W. And this gives me the relation straight up T max, and this is curly T max. So here's an example. We have constant coefficients. So it has nothing to do with distributions or anything like that. This is the most trivial example here. So if you write out the system, then you get, of course, 2 equations. And it's easy to see that if U is the vector 0, 1 and F is the vector 1, any function F2 here, then the pair UF is in T max. But the norm of U is equal to 0, while the norm of F is equal to 1. So we have 0 here and 1, I mean, non-zero here, which means T max cannot be an operator, because for an operator, of course, if your input is 0, your output has to be 0 as well. It is, however, a linear relation. So what I'm saying is, as soon as you deal with systems, you have to talk about relations rather than operators, unless you make some extra assumptions, perhaps. All right, now the minimal ones. So very simple. UF in T max is a subset of T max here. and if the support of U is compact in the set AB. And then we define the straight up T-min, just as we did up here. So if there's a pair in the curly T-min, then its classes are in T-min. And straight up T-min, of course, is a subset of straight up T-max. There's one other issue here, which one has to take into account, namely that the equation where f is equal to 0 may have solutions which have norm 0. So that's another thing one has to contend with occasionally, giving you a little bit of trouble here and there. All right, so now what are the results we have obtained? So these are in 3 papers. One has appeared in the Journal of Differential Equations. One is currently available only online. And a third one has been submitted last year. All right, so the first thing is existence of solutions. So we do not have existence and uniqueness of initial value problems, but we have solutions. They may not be solutions for any initial value problem, but there may still be solutions. So remember the set xi lambda, this is for fixed lambda, the set of bad x's where you have trouble. So if Q and W, let's assume here for now that Q and W are of bounded variation rather than locally of bounded variation, then there can be only finitely many such points. So we are right now only talking about solving the solution. We do that locally, so to speak. All right, so then between any of these 2 points, let them be ordered. Between any of these 2 points, we have existence and uniqueness of initial value problems. And therefore, you have a variation of constants formula, which is this one here. And there are coefficients Cj here. They are elements of C to the n, right? So you can always add a multiple for Cj equals 0. You have a particular solution, and you can add a multiple of the homogeneous solution here. Since this integral is left continuous, you want to look at the left continuous versions of your solution. So this is not the solution actually. You have to then take the balance. You have to balance this thing in order to get the actual solution. All right, and if you now have all these points here, then you have to look at all these vectors and they have to satisfy an algebraic system of equations. And then you get solutions. And what you get in particular, that you have at least n linearly independent solutions. So for the homogeneous case, you have at least n, but you may have more. You may have many. And in the case where we have infinitely many of these bad points, you can actually have infinitely many solutions, linear independent solutions of the equation, and they may be compactly supported. In the inhomogeneous case, we have several theorems, and one of them looks like this. So the inhomogeneous equation has a solution on AB if and only if this inner product is equal to 0. So if f is perpendicular to all the solutions of the homogeneous equation for the opposite lambda. And only for those v which vanish at both a and b. Now in the classical situation where you have existence and uniqueness of initial value problems, of course, if v is 0 at a, then it is identically equal to 0. And that makes this integral 0 for all f, which means you have a solution for all f. But this is not in general the case when you have bad points in the business. All right, so this is this kind of theorem is the main ingredient in this claim here that T min star is a differential operator, namely that it is T max. And since T min itself is a subset of T max, it shows immediately that T min is then a symmetric relation, not operator relation. So if you look at your favorite proof of how to do this, you always get T max is a subset of T min star, simply an integration by parts. So that works just as well here. For the opposite statement, 2 additional facts are required. And what you want is, you want to find the solution. If G is in the range of T min star, you want to find the solution of the DE. Right? It doesn't have to be, not quite yet, that VG is an element of T min star. You have to work for that. But first you want to obtain a solution of this differential equation. If you remember those proofs, the idea of the proof here is the same. You just have to take care of the problem that you do not have the existence of solutions in quite so generality. But it turns out that if G is in the range of T min star, then this theorem I had on the last slide or something like that will give you that you have in this case also a solution. But you don't have it for all G, but for those in the range of T min star, it still works. The other ingredient for the converse is that the orthogonal complement of K naught, these are the solutions of the homogeneous equation for lambda equals 0, that it's the range of T naught, which is this space here. So what you, to show that if F is in the orthogonal complement of K naught, excuse me, to show that it in the range of T naught, you have to show that it is a solution of such a differential equation. So again, you have to show that for such an F, you can actually solve the differential equation. And again, a theorem like I had on the previous page will do that for you. And this way we can show that T min star is equal to T max. So then we want to look at symmetric extensions. So I defined the deficiency indices earlier. And now I said we may have maybe infinitely many solutions of these differential equations, but it turns out that most, if you have infinitely many, that most of them have norm 0. So they don't count into the dimensions of d lambda when you look at these classes.
Rudi, can I ask, what do you mean by norm 0 here?
I mean that the inner product of u with itself is equal to 0. So u, the integral of u star wu.
Okay, thanks.
So we are living in a Hilbert space, right? These classes are elements of the Hilbert space. And of course, if you have a function u, then it is in the class 0 if its integral u star wu is equal to 0. All right, so what we can show is that the deficiency indices are still less than or equal to n, like they are in the classical case. So, and in the regular case, this is when q and w are bounded variation over the whole interval. Then we have that the deficiency indices are the same. And therefore, in that case, you always have self-adjoint extensions of T min. And they are, of course, as I said, they are less than or equal to n. They can be strictly less than n because of the other problem I mentioned. If you have maybe, again, solutions of norm 0. And then they don't contribute to the count of this n plus minus. All right. Okay, just said that. Now here's the theorem. So I should call it restriction theory rather than extension theory, because it's easier to think of restrictions of T max than to think of extensions of T min. So the symmetric restrictions of T max are characterized as follows. We call n plus plus n minus d. we have shown that D is finite. That's important here for us. And now you pick a number M, which is smaller than the smaller one of them. And then you pick D minus M pairs in Di plus D minus I, the deficiency spaces. So they should be linearly independent, and they should have this property. If you form these inner products, which by Lagrange identity you can write like this. This matrix here, so K and L run from 1 to D minus M. This matrix here should have rank D minus 2M. If that's the case, then this thing here, given by boundary conditions, so you take any pair in T max, but you ask that this condition here is satisfied, then this thing will be a closed symmetric restriction of T max. And conversely, all such restrictions are obtained this way. I should emphasize here that these are limits. So if U and G are in the domain of T max, then this product here always has a limit at both A and B. So these are limits here. So we always have, I mean, in the sense of limits, this does not mean you can evaluate that the U of B may not be defined, being only locally of bounded variation, U at the endpoint may not be defined, but these combinations here, they are defined as limits at A and B. So all the self-adjoint or symmetric restrictions of T max are given by these boundary conditions. So, and of course, if you have n plus equal to n minus, and if you choose M to B, then D is equal to 2 times n plus, and if you choose M equal to D over 2, then you get precisely the self-adjoint ones. This is if you have n plus equals n minus. Okay, I have 3 minutes. Now I come to the Eigenfunction expansions, which is the stuff I started with. For this, we need added hypotheses. I'm firmly convinced that these hypotheses are technical in nature. It's just that I'm not smart enough to remove them. I don't think they are actually relevant. Anyway, here they are. Lambda is the set of all those lambdas where you have where existence and uniqueness of initial value problems fails for some x. And it should be a closed and discrete set. It is a countable set always. It is a countable set. In this case, if it cannot be the full plane. In general, it could be the full plane, but since we have this condition here, it cannot be the full plane, then it is a countable set. But I also want it closed and discrete, and it should not intersect the real line. So then we can solve existence and uniqueness initial value problems for this equation. There's no lambda here. Lambda equals 0 is not a bad point, so we have existence and uniqueness for all these solutions here. And if lambda is not a bad point, and in the resolvent set, then we can write a representative of the resolvent in this form here, where there's a certain function m. These U guys here are fundamental systems of solutions, and this last term is not here if if W has no atomic parts, then this is not here. And under our conditions here, we have that these fundamental systems are analytic near R. They may not exist if lambda is a bad point. They may not even exist, but if they exist, then they are analytic, and they are analytic near R. And this here is, of course, this is a constant. This is analytic. So that means all the spectral information, remember the spectral information is where the resolvent has singularities. All those singularities are encoded in this function m. And this function is analytic away from R and lambda, as I said, and it is positive in this sense. In the upper half plane, its imaginary part is positive. And since lambda is a discrete set, then all the singularities where this is a problem, because lambda, m doesn't even exist, they are isolated, but such a function cannot have any isolated singularities, so they always have to be removable. Well, it can have isolated singularities, but they must be removable. And this implies that M is a Herglotz-Nevanlina function with this representation, and we have nu with the positive measure here. That's the important thing. A is a positive matrix, B is a Hermitian matrix. The important thing is that nu is a positive measure. I'm over time, but I'm also almost done. So this means we can now introduce the Fourier transform. It's defined like this. So for any function f, we compute this integral. We are really interested only in real lambda for this. And we then find that this Fourier transform is an element of L2 nu, and nu is this measure which was introduced here through the Nevanlina representation. So this is this positive measure. It comes up here again. Then you have compactly supported f. You extend this to all of L2W by continuity. This Fourier transform is not going to be unitary. It will have a kernel in general. This is the multi-valued part of T. T is our self-adjoint operator we are looking at, and H naught is the orthogonal complement of H infinity, which comes up next here. Maybe one more. This is the inverse Fourier transform. This is the Eigenfunction expansion. U, or certain combinations of U which are encoded in the measure nu, are the eigenfunctions, if you like. And then you get this integral here is the Eigenfunction expansion. So this is exactly what we did on slide 1 or 2. And if you restrict to H naught, then F and G are going to be unitary operators in this way. And as a final important thing you want for Fourier transform is that they diagonalize the operator T. So we have UF is an element of T. If and only if their Fourier transforms, the Fourier transform of F is given by just T times the identity function times the Fourier transform of F. So that is the last thing. And thank you very much for your attention.
Thank you very much.
Sorry for running over time a little bit.
It's perfectly okay. Absolutely.
We can always switch the computer off if we've had enough.
Oh, yes.
So any questions for the speaker?
So Rudi, can I ask about the set capital lambda, this mysterious set of values of little lambda for which you may have failure of uniqueness of solutions.
Mm-hmm.
So you assume that this has a trivial intersection with the real line, so it doesn't intersect the real line. Do you actually have any concrete examples where it is?
Where you froze?
Yes, I think Marco disappeared.
You
Okay.
froze, Marco, and now you're moving again. Do I have any concrete examples such that?
So, sorry, do you have any concrete examples in which the set of pathological lambdas is actually non-empty? I mean, you seem to be implying that you have any examples where it intersects the real line.
Yeah, so when you have n equals 1, then J has to be equal to I, and then you cannot, not going to intersect the real line. But for n equals 2, you can make plenty examples. And I have looked at examples where I have intersection of lambda with R, 2 intersections maybe, and I computed the M function, and everything works in those examples, but how to generalize I have not figured out yet.
So you know for a fact that this even can intersect the real line.
Yes,
so,
yes, you can make it.
Right, I see. So it's just that it messes up your proof when that happens.
So here's the example. If you take Q to be 0 on the diagonal, and n equals 2 2x2 matrices, and 2 or minus 2 on the off diagonals. And if you take J to be the usual symplectic guy, 0, -1, 1, 0, then you see immediately that you get determinant equal to 0.
Yeah.
For all lambda in that case, actually.
So in that example where you have capital lambda intersecting the real line, does the expansion theorem still work in that case?
I think it does, but I have no proof.
Oh.
So that's why on the next to last slides or so, I added these hypotheses, because that's where I have a proof. But I'm convinced that it is a technical question only. This should really work. This should really work in complete generality. I'm convinced of this. Yes.
Mm-hmm.
Do you have any intuition about how your technical restrictions might be removed?
We have been working here with one of my students, Stephen. We have been working on allowing for finitely many such points. And we have made some progress there. But when these points are, for instance, dense, then I mean, so as you saw in this, we have these intervals for fixed lambda, the bad points, the x's where something can go wrong, they have to be discrete, and you have these intervals where everything is good, and you can write down an variation by, variation by parts formula, and then you can do something. But if you have to deal with all lambdas at once, then the points can be dense where this happens, and you don't have any intervals, and I have not yet a good idea of how to deal with that. But we could deal with a case where we have intersections with R, but only finitely many.
Mm-hmm.
Then I guess we could deal with that.
So, more questions? Okay, that doesn't seem to be the case.
So I haven't been thinking about these things for a long time now. If you have locally integrable coefficients, you don't run into these problems, or you shouldn't. You have to assume.
If you have continuous locally integrable coefficients, means absolutely continuous measures. You run into none of these problems, even for singular continuous measures.
Right. Okay.
This happens only if you have atomic measures. So for singular continuous measures, you do have an extension theory and the Fourier and Eigenfunction expansion and so forth. Yes.
So of course, what you think about then is once you restrict yourself to the balanced things, it ought to work anyway, but it doesn't.
Well, the proof doesn't. I think it does, but the proof doesn't.
Mm-hmm. Okay.
So for singular continuous measures, there's no problem here. These problems which come up here are only if the measures have atomic parts.
Mm-hmm. On the other hand, if you want to think about difference equations, that's exactly what you have. Right?
No.
If you want to, I see. But surely, if you want to think about difference equations, you formulate them as differential equation means you have just Dirac measures in the coefficients.
No, I think you can get away without that. If you think, I mean, maybe in general, but if you think of a second order difference equation, you can, just like I said about the distributional potential, you can move things somehow in the off diagonals. These are the quasi-derivatives. If you formulate stuff in terms of quasi-derivatives, you can deal with second order difference equations without any distributions.
So if there are no further questions, let us thank the speaker again. So thank you very much.
All right, thank you very much.